Okay, let's take an example of how freefall works. Usually freefall is being used when there is an object in the air which is not subjected by any force except the one that actually creates that specific and particular acceleration. So a typical example would be the throw of a ball, basketball, football, any ball, which one would throw in the air, whoops, up, and the ball would go up and eventually would go down. Or for the case where an object is being dropped and the object is falling in one dimension from one position to the other, and this motion is due to the acceleration coming from the top, increasing the velocity as the object is falling down, or if the object is going up, decreasing its velocity because the acceleration is in the opposite direction as the velocity. So let's use and look at the case where an object is being dropped. Let's imagine that I am located at a particular distance above the ground. So I'm going to set up my coordinate system y. Let's say I'm right here. So this is going to be my position at t is equal to 0. And I will choose my coordinate system to be centered at the bottom. So initially, my position will be y naught. Say 100 meters. What I would like to know is what's going to happen to my object at t is equal to, say, 1 second. And then at t is equal to 2 seconds. So as I'm letting my object go initially, so at t is equal to 0 seconds, my position is y naught, which is 100 meters above the ground, and my initial velocity, or v naught y, is 0, because I'm letting the object drop without giving it any initial push or initial velocity. What's going to happen to my object? Obviously, the object is going to fall. And the reason why it's going to fall is because there is an acceleration that comes from the top coming down. Therefore, this acceleration will change the velocity of that particular object. Initially, the velocity of my object is 0. So if you look at this equation, you will see clearly that at t is equal to 0, my initial velocity vy is equal to 0. And therefore v in the y direction is equal to 0. As t is equal to 1, then my Vy will increase its magnitude. It will become minus g times 1. So this is telling us that at every second, the velocity is going to pick up the g value, which is in our case 9.81. So a second later, the velocity of my object will have picked up 9.81 meters per second. You can guess that 2 seconds later, you will replace this by 2. My initial velocity is still 0, therefore 2 seconds later, my velocity in the y direction will be twice 9.81. So every time you drop an object, you know that at every second, the velocity will increase or decrease by a magnitude of 9.81. If the object is going down, the velocity will increase because the direction of the velocity is in the same direction as the acceleration, like in this case. My velocity vector is coming down, therefore he has the same direction as the acceleration, therefore the velocity will increase. The negative sign tells us that the direction of the velocity is opposite to my coordinate system, down. And the value will be multiplied by 1, 2, 3 at every second. So after 1 second, the velocity magnitude will be 9.81 meters per second. At t is equal to 2 seconds, the magnitude of the velocity will be twice this. At t is equal to 3 seconds, the velocity will triple, etc., etc., etc. So at every second, my velocity will increase linearly. What about the position? Since we're now interested in the position, let's look at the equation that tells something about the position, which is the second one. We can use the same reasoning. Y is equal to y naught. In our case, y naught is 100 meters, so let's put it in. Plus v naught y. In my particular case, I decided to let the object drop, therefore this term is 0. Minus 1/2 times 9.8 times t, and this t is being squared. So what does that tell us? It tells us that after 1 second, the position, or let's start 0. At 0 second, you replace t by 0, therefore the last term is 0. Y is equal to 100 meters. We knew that. That's consistent. At t is equal to 1 seconds, then we replace t by 1, therefore y, the new position, will be 100 minus 9.81 divided by 2 times 1 squared. So after 1 second, the position will drop from 100 meters to, this is about 5, so roughly 95 meters. At t is equal to 2 seconds, we'll have the same initial position, 100, but this time we're going to have 9.81 divided by 2 times 2, which is now being squared. So that little square is telling us that at every second, the longer we wait, the larger will be the displacement. In this particular case, now we have a 4 divided by 2, a 2, so this is roughly 20. So this will be 80 meters. So on the first second, this particle had a displacement of roughly 5 meters. During the next second, the displacement has increased, which is now 15 meters. And it's going to get bigger and bigger and bigger. So that's the main distinction between velocity and position for a free fall, or for the case where a is not equal to 0, and specifically roughly equal to 10. At every second, the velocity will pick up the magnitude of 9.81. However, and this is a linear progression. However, the position, just by this equation, it's clear that it's not linear because there is a polynomial of a second degree. The position or displacement will increase the longer you wait. So that was for the case where you drop an object. Let's imagine now you throw an object up. So you start from the ground. You're going to give, let's say, this particle an initial velocity up of 100 meters per second. You will start the process at y naught is equal to 0 to simplify the algebra. Let's see what's going to happen. A second later, what do you expect the velocity to be? You know that the velocity will be the initial velocity minus gt. Therefore, a second later should be the initial velocity minus 9.81, roughly 90 meters per second. Similarly, at t is equal to 2 seconds, now you have a factor of 2 over here. Therefore, this will become 80. So a second later, the velocity will be up with a magnitude of 90 meters per second. 2 seconds later, the velocity will be smaller, of a magnitude of 80 meters per second. 3 seconds later, 70 meters per second, etc., etc., etc. I'm using 10 to make life simpler instead of 9.8. So roughly, if we consider in this case 10 instead of 9.8, you know that after 10 seconds, this ball will reach its maximum position and eventually will start to fall down. So at t is equal to 10 seconds, Vy will be 100. And again, if I'm using g as 10 to make my algebra simpler, I would end up with 0. That's going to be my turning point. What's going to happen after that? Let's increase time. Vy is going to be 100 minus 10. Now at 11 seconds, what's going to happen? Now I end up having a negative number. This is telling me that now the velocity has increased again, but the direction has changed. So now the ball is going to fall back down. 11 seconds, its velocity will be minus 10. At 12 seconds, minus 20, etc., etc., etc. Therefore, 20 seconds later, the velocity should be exactly the same as the initial velocity, but in the opposite direction, minus 100 meters per second. So our little object will go and then again, we can do the exact same analogy with position, and we could calculate the position at every instant. We will see that as the object is going up, it will travel a large distance initially, but as time passes by, since the acceleration goes against the initial velocity, the velocity decreases, and therefore the displacement will also decrease. So as the ball goes up, it will travel less and less distances for the same amount of time every second. And then as the particle comes back down, again, the distance will increase as the time increases again. What about the acceleration? We know that the velocity decreases as the object goes up. So as the object goes up, the magnitude of the velocity decreases. And the direction of the velocity is up. As the object is going down, we know that the magnitude of the velocity increases again, and this time its direction is negative. The acceleration, again, remember, free fall, which means that the acceleration is always, always, always 9.81 meters per second squared in the j direction. So at this particular time, t is equal to 0, after you give it an initial velocity and that you let the object go, the acceleration of this object is 9.81. 1 second later, still 9.81. At 3 seconds later, still 9.81. So at every time along this process, this particle has an acceleration coming down of 9.81 meters per second all the time. As the particle goes up, this is this particular acceleration which will minimize and change the magnitude of the velocity. Because remember, by definition, whenever there is an acceleration present, it will change the velocity. So as the object is going up, it's going to be the magnitude that will be changed, and it will be decreasing and decreasing and decreasing. As the object is going down, now this acceleration is in the same direction of motion, therefore now it will increase and change the magnitude of the velocity. And it will increase its magnitude, making it bigger and bigger in the negative direction. What about the top? If we zoom the top, we're going to see something like this. Let's neglect this direction. I'm just spreading out so that it's a little bit clearer. Here we have velocity going up, then we know that the velocity magnitude gets smaller, 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 and at the top the velocity vector should be 0. We have the 0 vector. Then an instant later, the velocity will pick up a little bit of a value, this time opposite direction. Then its magnitude will increase because the acceleration is coming down, etc., etc., etc. So if we take an interval which is very, very close to the tipping point, we will see that magnitude-wise, the magnitude of this point, or the magnitude of the velocity at this point and this point, are exactly the same. Similarly, the magnitude of the velocity of this point and this point are exactly the same. Again, as you reduce the interval, the magnitude of the velocity equidistant time about the tipping point are always have the same magnitude. So in this case, the acceleration doesn't change the magnitude of the velocity. However, we notice that on the left-hand side, or before that particular interesting point, the direction of the velocity is always up, while after, it's always down. Therefore, at this particular top position, which is the top of the parabola, there is still an acceleration, and this acceleration causes now the direction to change. The velocity magnitude is not being altered at this particular position, but what's going on is that the velocity vector and the velocity direction will be shifted. And for this to occur, for the particle to go from one direction to the other, there's got to be an acceleration to change that velocity vector. So between all the points on the way up, this acceleration, which is always down, will cause the velocity magnitude to decrease. As the object is coming down, this same acceleration will cause the velocity magnitude to increase in the opposite direction. At the tip of this little parabola, this acceleration is still present. So here, even though the velocity is 0 in magnitude, there is still an acceleration, which is again minus 9.81 in the j direction. At this particular time, the role of that acceleration will be to flip and change the direction of the velocity. So keep in mind, when we write this, since v is a vector which has both magnitude and direction, sometimes the acceleration will change the magnitude, making it bigger or making it smaller. Sometimes it will not alter the magnitude, but it will change the direction. And that's what's happening at the tip of that little parabola. So keep in mind, whenever you're free fall and an object is falling down or going up and then falling down again, at every instant of that path, the acceleration of the object is 9.81 in the negative direction, going down, regardless of the value of the velocity. To see this clearly, we could plot position versus time, our favorite diagram for such a motion. We would start at y is equal to 0, and as time increases, the position will increase, it will increase, it increase, and then it will decrease, 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 and fall back to the ground. This needs to be proportional to t squared, as we already knew from this equation. If you want to draw the velocity in the y direction versus time, you know that you only have to take the first derivative. This will be the point where your velocity vector will cross the x-axis. The velocity starts at a high value, which is the value that we needed to have to get it off the ground, in this case 100 meters, and it will that's not very straight. And the velocity will decrease its magnitude linearly such that the slope is the actual value of our acceleration, minus 9.8. So a second later, if the velocity started at 100 meters per second, a second later, the magnitude of the velocity would be roughly around 90 meters per second. 2 seconds later, it would be roughly 80 meters per second, and so on and so forth. At this particular point, the velocity happens to be 0, and that was the tipping point right here. But this point is no different from this point or this point or this point. The acceleration is still 9.8 because the slope hasn't changed. Therefore, now if you want to plot the A versus t diagram, obviously this will just be the value of the slope, which is constant.